Welcome to the Deep Dive.
Oh,
Today we're doing a really critical analysis. It's part of our series Inside Quantum AI, which is brought to you by the team over at LoopQuantum.AI Labs. That's LoopQuantum.AI.
and our mission today is pretty fundamental. We're going to dig into why the current big AI models are, well, failing to scale, and more importantly, explore the quantum physics that's needed for the next big leap.
Okay, so let's get right into it. We know that Loop AI Labs, they've been in this space since 2012, and they actually predicted that today's big models, the transformers, would eventually slam into a brick wall.
Exactly. And that wall, it isn't about better chips or more data. It's entirely mathematical. It all comes down to a core mechanism called self-attention.
Right. Before we get lost in the math, what exactly is self-attention for someone who might not know?
It's basically how the AI weighs every piece of information against every other piece of information in its context window.
Can you give us a quick way to visualize what that means for the cost, for the computing power?
Sure. Imagine you're reading a 100-page document. Now imagine for every sentence on page 1, you have to cross-reference it with every single sentence on pages 2 through 100.
That sounds incredibly slow.
It is. And that relationship creates what we call quadratic complexity.
And
Huh.
but what on A means in practice is, well, it's brutal. If you just double the input size, the context, the computing cost doesn't double, it quadruples.
It's quadruples. And if you double it again, it goes up 16 times.
So scaling becomes just astronomically expensive, almost impossible for really complex things.
Exactly. This is why current AI is sort of stuck with simple queries. If you want to simulate something truly complex like the human body or the climate, you need billions, maybe trillions of tokens.
And that really puts the problem into scale. I saw an example about modeling just a small part of a fingernail.
Yeah, the complete cellular state of, say, 100 million cells in a fingernail would need something like 500 billion tokens.
500 billion. And today's biggest models, what do they max out at? Maybe a couple million tokens.
If you're lucky. Gemini is around 2 million, I think. We are nowhere close.
So this isn't just about building faster chips.
No, it's a fundamental mismatch. I mean, classical hardware is deterministic. One input gives you one predictable output.
But reality isn't like that.
Not at all. Reality, chaos, biology, the universe, it's all fundamentally probabilistic. We're trying to simulate a probabilistic world on a deterministic machine.
It's just not feasible.
It's not. And that's why the core belief at Loop AI is that we need a quantum reboot, a totally new architecture. We need something that's quantum native.
So quantum native AI, this isn't just about running the same old algorithms on a faster quantum computer, is it?
No, not at all. It's a completely new kind of architecture. And to understand how it breaks that quadratic barrier, we have to look at the one thing in the universe that just doesn't play by classical rules.
Superposition.
Superposition. And the best way to grasp that is to go back to maybe the most famous physics experiment ever, the double-slit experiment.
Ah, yes. 1927, the experiment that basically broke physics. So the setup is simple. You have a gun that shoots electrons, a screen with two tiny slits, and a detector wall behind it.
Right. And if you think of electrons as tiny tennis balls, you'd expect to see two simple vertical lines on the detector, right? One for each slit.
But that's not what they saw. Not at all.
No. They got an interference pattern, like when you drop two stones in a pond and the waves overlap, creating peaks and troughs.
But the truly bizarre part,
Right.
they got that pattern even when they fired the electrons one at a time.
Exactly. It meant that a single electron was somehow going through both slits at the exact same time and then interfering with itself, like a wave.
Which makes no sense. But then it gets even weirder. When they put a detector at the slits to see which one the electron actually went through,
The interference pattern vanished.
it just disappeared. The electron went back to acting like a normal little tennis ball, creating two simple lines. It's like the universe is gaslighting scientists.
It really is. And the conclusion from this is just profound. A particle isn't a solid thing until you look at it. Before you measure it, it's a probability cloud. It exists in a state of superposition.
Meaning it's literally in all possible places at once. Observation doesn't just see reality, it creates it.
It actively creates it. And that weirdness is the key to breaking the ON problem.
So connect those dots for us. How does a particle being in two places at once solve AI's scaling crisis?
Well, in a classical computer, to compare n things, you have to do n squared separate checks. But in a quantum system, a single quantum bit of qubit can exist in a superposition of states. It can be a 0, a 1, and both at the same time.
So you're encoding way more information in the same space.
Vastly more. Instead of checking every relationship one by one, you can effectively calculate multiple answers simultaneously. You're no longer bound by that one-by-one quadratic march.
You're jumping from ON scaling to something more like linear.
Or even better, potentially ON, or even logarithmic, O log n, against the context size. It's a total game changer.
So if classical AI is about learning patterns from data,
then quantum native AI is about understanding reality at its most fundamental probabilistic level. It's engineered to work the way the universe actually works. And that's what lets you model the kind of complexity that classical AI just hits a wall on.
that is genuinely a radical shift in thinking. So it's not just a faster processor.
It's not. It's a parallel reality engine. You're no longer checking every single relationship one by one, which is what creates that horrible quadratic curve.
And if you build an AI that truly mirrors reality in complex chaos, the line between an accurate simulation and reality itself,
Oh, it gets incredibly
then that's something to think about.
It is a radical and I think necessary shift. And thank you for listening to this deep dive in our Inside Quantum AI series.
We are absolutely committed to this. At LoopQuantum.AI Labs, we're bringing together quantum physicists, theoretical neuroscientists, and AI architects.
All of them focused on solving the intractability of complex chaos.
You can join the research lab and see what we're working on at LoopQuantum.AI.
And please check out the next deep dive in our series.
It'll be available soon on X. We'll catch you next time.